All right, let's finish section 7.3 by looking at the definite integral in another way. All right, the total change. Suppose that f of x gives the rate of change of capital F of x. Okay, so this f of x is like the derivative. Then f of 2 gives the rate of change of capital F at 2. F of 3 gives the rate of change of capital F at 3, okay, at specific instants. If we wanted to find the total change rather than just the rate of change at a moment for the function capital F of x from this interval 2 to 3, we could divide the interval 2 to 3 into n equal parts, using each part as the base of a rectangle as we did before. Okay, the sum of the rectangles using left endpoint heights, for example, would approximate the net total change of f, okay, as long as you have that function that we're working with is the rate of change function for capital F. Okay, and then the limit as this sum as n goes to infinity would give the exact total change of capital F. Okay, very interesting there. This means that the total change in a quantity can be found from the function that gives the rate of change of the quantity using the same methods that we use to find the area under a curve. Okay, very, very interesting there. Okay, so let's formalize this a little bit. The total change in f of x. So if little f of x gives a rate of change of f of x, okay, so this is a rate of change function. Very important to keep that in mind. Okay, of f of x for x in a to b, then the total change in capital F of x as x goes from a to b is given by that exact same formula we have for the definite integral. Okay, same formula there, and so it's a different interpretation of the definite integral. This can give us the total change. Now, earlier in this section, we were doing area for the definite integral, and that was only really making sense to call it area if our function was always positive or always above the x-axis. But for total change, if you've got some kind of a function that's going up and down and all around, you could have negative values that come out. You could have a total change is where the function actually dropped overall on the interval. So we're going to get into a little bit more detail with the interpretations in section 7.4 for total change versus area versus all of these different concepts. But very, very interesting here. Another version, another interpretation of this definite integral here. Okay, so the rate of change, if you're given a rate of change, then you can do that definite integral. And then, yeah, again, it's no accident that this is like an S-type symbol for summation. This should be this should also be looking a little bit like antiderivative, right? And so we're going to tie all of these kinds of concepts together with this definite integral and antiderivatives and derivatives all being related to each other in certain ways. And that's going to be an extremely exciting thing that we're going to cover in section 7.4. So I hope you're excited about that. All right, so let's look at example 4 here. A patient is receiving intravenous therapy where a saline dextrose solution is administered by a machine that automatically adjusts the rate based on the patient's metabolic needs. The following chart shows the rate, okay, rate at which the solution is administered in milliliters per hour for each hour during an 8-hour period. Approximate, okay, so again, we're still approximating using like a rectangle system, okay? We're not using the actual like limit as n goes to infinity thing yet. Okay, so we're still approximating with rectangles. The total amount of solution administered during this 8-hour period. Okay, so we've got this total change situation where we were given a rate, okay? We were given a rate, and we're trying to find the total change in the quantity of the solution itself. So what we want to do is we want to think about this as dividing it up into all of these different rectangles over this 8-hour period. So it's probably a good idea to try to interpret this chart here in terms of areas of a bunch of little rectangles. And this isn't really given to us as a continuous function. We just have certain little points here. Now, supposedly this machine is just like, dripping this rate at a continuous and, changing the rate continuously, or administering the solution continuously, but we only have information for these certain hours here. So as I draw a picture, it's not going to be like some continuous curving function. We just have a few different points. Okay, so we've got all of these different things down here for time. We've got hour 0, and then we would have like 1, 2, 3, 4, 5, 6. We have hour 7, but this is supposed to be over an 8-hour period, right? And that just makes sense because hour 0 doesn't really make sense to call it hour 0. That could be like hour 1. But anyways, there are a total of 8 separate hours that we're considering. So what I'm going to do is I'm just going to plot each of these based on the information that we have. So not going to be super crazy accurate, but I just want to get a visual aid going here. So at hour 0, we had a rate of 24 milliliters per hour. So I'm just going to go up here and say, oh, I don't know, how about 24 is like right here? Okay. And they didn't really tell us to use left endpoints or right endpoints or midpoints, but it's looking a lot like over this 8-hour period, since I was given 0 off on the left side here, it's looking a lot like left endpoint to me. So if I would do a rectangle that went across for that first hour right there, then it could be left endpoint right there. Okay, then we want to do at hour 1, 2, 3, 4, 5, 6, 7. Okay, so at hour 1, it was up here at 26. And I would do left endpoint again. So I'll just label that right there as a height of 26. Okay, hour 3, or hour 2 now, we were at 21. Okay, so a little bit lower. I'll go right there is like 21. And again, it looks like we're doing left endpoints because of the way this chart was given to us. Hour 3 was at 29. Okay, so again, a left endpoint there. Okay, hour 4 was at 33. And a bunch of left endpoints going on. Hour 5 was at 37. Hour 6 was at 28, so coming back down. Hour 7, 25. Okay, and then hour 7, that information at hour 7, that like covers that whole last hour, that whole 8th hour. Okay, so the way that this worked out, it's not necessarily a continuous function, but you could imagine that maybe you could draw some kind of curving line that would somehow approximate all those points, but we don't have all of the information in between. So all we really have here is we know that the width of each of these is 1, and we know that we're adding them all up using left endpoints, but it's not even really that much more complicated because we don't have a function, but we already know what the function values are at all of them. So this one's actually not too bad at all. We have that the total change or the total amount of the solution would be found by just adding up all of these different rectangle areas over this 8-hour period. All right, so yeah, the total length of time here is from 0 to 8, but we were given these informations at left endpoints. Okay, so let's see, how should we word this? The total amount of solution. Okay, so the total okay, it's just length times width. Okay, notes that the width of each rectangle is 1. So that was not too bad because we had just every hour was given to us. It could be different. It could be given to us as every half hour or quarter hour or something like that. Okay, but the width is just 1. And then it's also important, this was in milliliters per hour. So all of our units are lining up with each other. So no tricks are involved. Okay, so the total amount is just going to be length times width on all of these. So I'm just going to write it as 1 times, and then it's left endpoints. Okay, so all these values from the table, 1 times 24 plus, and then just all of these different values, 1 times 26 plus 1 times 21 plus 1 times 29 plus 1 times 33. All of these different rectangles. And it's just a times 1 each time. Okay, and kind of interesting. I mean, I don't know if this is a real situation, but for whatever reason, it looks like the patient had a higher metabolism perhaps right there and needed more. Maybe it was meal time. I don't know. All right. Anyway, so total amount would just be add this all up. So we've got 24 plus 26 plus 21 plus 29 plus 33 plus 37 plus 28 plus 25. And I got 223. And this is milliliters, and not per hour or anything like that, because the per hour was the rate that was given to us. And with this process, we found a total amount. Okay, so the total change, and this makes sense that this comes out this positive number because all of the rates were always positive numbers too. Okay, any of those rates being negative wouldn't have made sense unless this machine was like sucking solution out of the patient. Okay, so this could only make sense that this answer is positive. Okay, and yeah, that's in milliliters, total milliliters over this 8-hour period. Okay, and then just to be, just to really familiarize ourselves with all of the notation, because it's important to interpret everything. If I could spell, I want to just say mathematically. We could write, okay, using that definite integral notation, we could write that the total change or the total quantity that we have here is from 0 to, be a little careful because this 7 is a little bit misleading. We did this full 8-hour period, and that 7 was just given to us as like this left endpoint value. Okay, but we actually did an entire 8-hour stretch, okay? And this table was giving us left endpoints. So we could write 0 to 8 because we are covering all the way through, okay? Hour 7 goes up until the 8th hour, okay? So we are covering a total of 8 hours here, okay? And so whatever the function is, we could call this like f of x if we wish. And then it comes out to that number. Okay. So just want to keep that in mind. And then, yeah, we're going to tie this concept of the definite integral and the indefinite integral, derivatives and antiderivatives, all kinds of exciting stuff in the next section. So I'll be very excited for section 7.4. Okay, but for now, that finishes off section 7.3. Hope you have a good day.